All right. So first off, thank you to the organizers for organizing this conference and for inviting me to speak. I'm really looking forward to the discussions in a few weeks' time. So my name is Aurora Ireland, and I'm a postdoc at Stanford University. And today I'm going to be telling you about B-mode polarization in the CMB from cosmological phase transitions. So I want to start off with a quote. I just pulled it from a random paper, but honestly, you'll find quotes along these lines in many papers. And the upshot is that B-mode polarization in the cosmic microwave background is a smoking gun for inflation. Um, so inflationary models pretty generically predict a scale invariant spectrum of tensor perturbations, and these are going to induce a characteristic B-mode polarization pattern in the CMB. There are, of course, other sources of B-mode polarization. Namely, you can have gravitational lensing, which converts E-mode polarization pattern to B-mode. Dust or foreground noise will also give you some. And as it stands at the onset of this project, inflation was really the only known direct primordial source. So here we have the angular spectrum of well, B-mode polarization, but it also shows E-mode and temperature. So here we have the prediction from inflation for a tensor to scalar ratio of 0.03 and 10 to the minus 3. The inflationary signal famously has this recombination peak at a multipole moment of 100, and then on larger scales, it's got the reionization peak. And then we also know what the lensing B-mode signal looks like. Peaks on smaller scales. We also have some data here. So these are the known sources. In principle, though, really any source of large-scale coherent tensor perturbations that was produced before reionization can contribute to B-mode polarization. And the source I'm going to have in mind for this talk is first-order cosmological phase transitions, which source tensor perturbations in 3 stages. So these generically predict peak power on smaller scales because they happened in the earlier universe. But even though they predict peak power on small scales, they do have a white noise spectrum on larger scales, which famously has this k cubed causal scaling. And because of this, naively, you would expect the contributions from phase transitions to be negligible, namely because the CMB is sensitive to long wavelength modes or large scales. So, co-moving wave numbers of about 0.01 inverse megaparsecs versus for the phase transition, power is going to be suppressed on these large scales. In particular, the super horizon scaling for the dimensionless tensor power spectrum goes like k tau star cubed, where tau star is the conformal time at the time of the phase transition. And for initially super horizon modes, this is much smaller than 1. So things are going to be suppressed on the scales that the CMB cares about. And for this reason, you would expect it to be negligible. I wanna make the case that that's actually wrong. Actually, we find that tensor perturbations from a phase transition can produce a B-mode signal whose strength can rival that of, inflationary predictions that we hope to test soon. However, because the spectral shape is distinct with more power on smaller scales, you can still distinguish the scenarios. And also the phase transition is gonna come with a complementary gravitational wave signature that you can use as a cross-check. All right, so that was the motivation. We're gonna do a lightning review of B-mode polarization and how that gets baked in. So generically, scalar and tensor perturbations in the early universe are going to source temperature anisotropies, and quadrupole anisotropies are going to get transformed into linear polarization of scattered photons when they scatter with free electrons. And this is my little picture of that. So it's convenient to decompose the resulting polarization into divergence and curl parts. The divergence part is the E-mode polarization pattern, in analogy with an electric field. And this is the part that's parity even, it's unchanged under reflection, and this is sourced by both scalar and tensor perturbations. B-mode polarization is the curl part, in analogy with a magnetic field, and this one is parity odd and sourced by tensor perturbations only, which is why we say that detection of a B-mode polarization signal would be evidence of gravitational waves or tensor perturbations. I'm not going to go through actually how to calculate the observable we're interested in, which is this angular spectrum of B-mode polarization, but I'm at least going to say schematically how it's calculated. So we start out with the tensor perturbation Hij, which is going to enter into the temperature anisotropy. That's going to enter into the CMB polarization tensor, excuse me. You're going to decompose that into gradient and curl parts, and you're going to expand in spherical harmonics on the celestial sphere to isolate these coefficients, which enter into your angular spectrum of B-mode polarization. This is the full expression for how you calculate them. And if you actually go through the whole song and dance, you can show that this is equal to an integral over log k of the dimensionless tensor power spectrum times this FL function, which is this horrible mess. You can see our paper for a little bit more discussion of what all this is. The way to think about this f of L really is just as a window function that picks out the modes that the CMB cares about. It's going to peak roughly around 0.01 inverse megaparsecs, and going to have moderate support on larger scales, but drop off very sharply on smaller scales. Okay, so in writing down this expression, I've implicitly decomposed my tensor perturbation into an initial amplitude times the transfer function, which is going to capture all the time dependence. This is useful because now I've got my statistical correlations that are specific to whatever particle physics model I'm interested in, separated out from the deterministic evolution, which is captured by the transfer function. The main thing to know about the transfer function is just it's initially constant until the mode enters the horizon, at which point it becomes this super oscillatory thing. Okay, so now we're going to talk about how to calculate the tensor power spectrum from the phase transition. So first order phase transitions proceed through bubble nucleation. So a bubble of true vacuum nucleates in the metastable vacuum. And these grow and collide and eventually come to fill the whole space. And throughout this process, it's going to source tensor perturbations in 3 stages. In the first bubble collision phase, you're going to break spherical symmetry, and that's going to allow the gradient energy of the scalar to source anisotropic stress. Next, so even after all the bubbles have collided, you're still going to have shells of fluid kinetic energy that are going to continue to propagate and collide. That'll also source tensor perturbations, and then also give rise to things like vorticity and turbulence that can also source tensor perturbations. But we're really just going to focus on the first source, the bubble collision stage. We're going to consider a supercooled phase transition, which has negligible plasma friction and a runaway bubble wall. And for this sort of phase transition, your dominant contribution is going to come from the bubble collision stage. Right, so the first thing we need to do is we need to solve the wave equation for our tensor perturbation. Here, this is conformal Hubble. The primes are derivatives with respect to conformal time. And this pi ij is going to be our source, which is the Fourier transform of the transverse traceless stress tensor. It's a homogeneous isotropic random variable. And then the other thing to know about it is that it's short-lived in the sense that the phase transition completes within a Hubble time. So during the phase transition, because it completes quote unquote fast, we can neglect expansion and just solve this equation, which can be solved via the method of Green's function. And we have this expression. After the phase transition, we no longer have a source, but we can no longer neglect expansion. And we have this expression. You can solve for these coefficients by matching the two at the end of the phase transition. And now, because of a subtlety with the superhorizon spectrum, I'm going to have to treat the subhorizon and superhorizon modes a little bit separately. So in the subhorizon regime, we can identify the initial amplitude as just this Hij evaluated at the end of the phase transition. And then you can compute that the dimensionless tensor power spectrum is this, where I've really hidden all the physics in this delta function, which is defined like this. I've pulled out all the thermal phase transition parameters, including the efficiency factor and the transition strength. So really this just depends on this ratio of K on A star beta. Here, this is the unequal time correlator, which is like a 2-point function of the two source terms at two different times. And the reason for us focusing on this source is because Gino and Takamoto have this wonderful paper where they compute delta semi-analytically. So they actually go through and they compute like the 2-point function of the stress tensor for this source. In particular, in the subhorizon regime, it just has this scaling, and so we can plug this in and we get this expression for the subhorizon tensor power spectrum. In the superhorizon regime, this is where the subtlety comes in, which we didn't initially appreciate. So because activating a superhorizon mode is kind of like exciting an overdamped oscillator, you actually need to wait a little bit. You need to wait some small but finite time epsilon for it to reach its maximum amplitude. And only then can you apply the transfer function. So we're actually going to define the initial Hij as Hij at the end of the phase transition plus some small amount of time for it to finish growing. And then this case, this is the expression you get, which it looks just like the subhorizon one, except there's no AH over K squared piece. And then also this delta, this has a different scaling in the superhorizon regime. It was like x to the third. And so at the end of the day, this is the expression that you get for the superhorizon dimensionless power spectrum. So famously, this has the expected k to the third causality limited scaling, which means it's white noise. By causality limited, I just mean those modes that have wavelengths that are much larger than the spatial correlations of the source. And because of that, it's kind of like universal behavior. They're not really sensitive to the microphysics. And so their correlations are just random white noise. And then also because K tau star is much smaller than 1 for these initially superhorizon modes, this is suppressed, again, as expected. So the full spectrum is the combination of these things. This is a superhorizon piece, this is a subhorizon piece, and I should note that when we derive the spectrum in the superhorizon tail, we make some approximations, so it doesn't hold all the way up until the peak. So in the intermediate region, we just have some interpolating function. The peak itself is set by the max bubble size and has this expression. So this is what it looks like. So here I have two benchmarks. For the phase transition, for both, I'm going to take the efficiency factor to 1 and beta over H star of 2, which is consistent with a supercooled phase transition. And then the green benchmark is taking place kind of pretty late at 1 EV in the visible sector. I should note that this should probably be taking place in a dark sector. But the time in the visible sector will be 1 EV, and the phase transition strength will be 3 times 10 to the minus 5. The red one will be taking place a little bit earlier at 3 keV and with a strength of 0.05. And then these are compared against the inflationary nearly scale invariant spectrum with a tensor to scalar ratio of 10 to the minus 3. Right. Oh, I should also add that the CMB sensitivity, this is roughly, you should think of this as that domain of support for that f of L function. So recall that the CL was this integral over P sub H times this f of L. So this is the region that you're sampling from the power spectrum. So for the green benchmark, you're sampling from the superhorizon tail, the peak, and a little bit of the subhorizon tail. Versus the red, we're just going to get contributions from the superhorizon tail. Okay, and now we can finally look at our B-mode polarization spectrum. So this is for the 1 electron volt benchmark, and we chose these parameters so that way it would match the maximum amplitude of the inflationary spectrum. So which you can see here, and on larger scales and smaller scales, the B-mode spectrum is going to have less power. And you can kind of understand that if you look at this, because as compared with the nearly scalar invariant inflationary one, this has less power. So kind of makes sense. You can see how the shapes kind of translate. This is our 3 keV benchmark, which here we're just sampling from the superhorizon tail. And here we see that it has more power on smaller scales and less power on larger scales when compared with the nearly scale invariant inflationary prediction. You can kind of see here is a color map of the phase transition B-mode predictions for various T star. And you can see as you lower the temperature and you start sampling from the peak and the subhorizon tail, how the shape changes. And then also on this plot, I have the inflationary prediction that matches the current bicep limits as well as optimistic CMBS4 sensitivity. This is how to understand the spectral shape, which I think I've already commented on. So I'm going to skip that in the interest of time. I do want to mention that this scenario has a complementary signature in that the same tensor perturbations that are giving you your B-mode polarization are also going to contribute to the stochastic gravitational wave background. As parameterized by this spectral density parameter, which you can calculate in this way. It has a very analogous form to the dimensionless tensor power spectra. Right, so this is what it looks like. So here I have the same red benchmark as before, the 3 keV one. This is the 1 EV one. And then also I have the inflationary prediction. You can note that they all cross around a frequency of 10 to the minus 17 hertz, like you would expect. And then the red benchmark is maybe within range of the square kilometer array. So yeah, what I mainly want to say with this is this gives another way to break the degeneracy with the inflationary signal, because if you look and you see a B-mode signal, but you don't see the complementary gravitational wave signal, then you can say it's inflationary. Okay, in the last minute here, I just want to wrap up. So in summary, I've shown that tensor perturbations from a first order phase transition can produce B-mode polarization on observable scales if you have appropriately chose phase transition parameters. In particular, you're going to need a late time, pretty strong transition. And this could potentially be testable with CMBS4. Because the spectral shape is distinct for the phase transition, you can, if you make measurements on multiple scales, you can differentiate this from the inflationary scenario. In particular, the phase transition is usually going to have more power on smaller scales if it's happening in the early universe. And then you can also use the gravitational wave signal as a cross-check. In terms of future directions, the number one thing I want to do is I want to make these phase transition parameters, I want to see if these can come out of a realistic particle physics model, because that would be interesting. And then you could also look at other sources of tensor perturbations. Here we just focused on the bubble collision stage, but you can also have them from the sound wave and turbulence phases, from cosmic strings, domain walls, and then also just setting some limits on late time phase transitions because I was surprised how few there were. Okay, thank you.